This is my first visit to the Newton Institute, and I was telling Nick Evans that when I wandered in on the weekend, I thought I'd wandered onto the set of the Teletubbies because of the modern architecture and all the grass around.
Oh, you mean CMS, right?
The whole thing. Sorry, the whole thing. Yeah, the whole thing. Yeah. I have little kids at home, so we are forced to watch the Teletubbies all the time. So the title of my talk is Curved Space, Monsters, and Black Hole Entropy. I apologize to anybody with a mathematical bent who saw this and thought maybe I would talk about the monster group. There's no monster group in this talk. Monster here refers to a configuration which we build which has an exceptionally large amount of entropy. And we call them monsters because they have some pathological properties. So anybody who came for the monster group will be disappointed. And the level of the talk will be quite pedestrian and not very mathematical. So let me start by just saying a few words about black hole entropy. By now everybody knows this formula that the black hole entropy of a black hole is equal to its area divided by 4 in the proper Planck units. One way to think of this is that there's about 1 bit of entropy per Planck area on the surface of the hole. My favorite mnemonic for remembering why this is true comes from this simple thermodynamic formula for entropy. So ds is dq over t. If you plug into this that the size of the black hole is of order its mass in Planck units and that the temperature is of order the inverse size in Planck units, then you can just do this integral and you see that it scales like r squared. So that gives you an area law. It doesn't explain what the meaning of this entropy is, but it gives you the result. So what is the conventional meaning of entropy? Normally we think of it as the log of the number of microstates consistent with some macroscopic condition that we place on the system. So in my way of thinking, without some type of coarse graining, there's no entropy. Typically we have a number of different microscopic configurations which fit into some category. We forget about which particular microscopic state we're talking about, and we just talk about the category, and then the entropy of that category is a log of the number of microstates. Typically, we tend to think of entropy as extensive. So if I have, for example, a lattice a regular lattice in some volume V with c degrees of freedom per lattice site, then typically the number of microstates is c to the v, and if I take the log of that, I get something which scales as v. So that's why it's a little bit surprising that we get an area rule for the black hole entropy. Another useful way to think about entropy is that if you have a Hilbert space and it describes some volume v, and for example, I could have as the degree of freedom on each lattice site a qubit, then the dimensionality of the Hilbert space goes like c to the v, and so the entropy actually scales with the number of degrees of freedom. So that's another way to think of the entropy.
Looks a lot better for fermions and bosons.
Yes, right. So let me discuss something which I call the 't Hooft bound, and it's kind of a poor man's approach to holography. So let's imagine that you have some criteria for gravitational collapse, and in general relativity this goes by the name Hoopt conjecture. And what's found, there's no proof of this, which is why it's still a conjecture, but it's found for astrophysical systems and also even for very exotic situations where, for example, you have particles colliding. If you confine an amount of energy E into a region which is smaller than that energy in Planck units, then that system will evolve into a black hole. So if something becomes so dense that it violates this inequality, then it will evolve into a black hole. So what 't Hooft did was he said, let's take a box, a system say in a box, and let's look at configurations of matter in that box which are on the verge of collapsing to black holes, but they're not quite black holes. So they're just on the verge of, they just saturate this inequality. Now, to estimate the entropy of all the possible configurations which just saturate this Hoopt conjecture, first you need to notice that for a typical system which is under some kind of energy constraint, the dominant, that defines some surface and phase space, and the dominant type of system on that slice of phase space is a thermal system. In other words, if I neglect non-thermal systems, I make an error in computing the entropy which vanishes as the size of the system gets large. So it's fair to in order to estimate the entropy of systems which saturate this bound, it's fair to just consider thermal systems. So he does that, and then you get a very simple formula for the total entropy. It's just the entropy density T cubed times the volume. For the total energy, you get T to the 4th times R cubed. When I plug in this inequality, I combine this equation with the inequality. I can solve for how T scales with R. T goes like R to the minus a half. And when I compute the entropy, I get that it scales, or an upper bound on the entropy, and it scales like A to the 3/4. So you get this bound.
So you're ignoring all gravitational interactions.
I am. So the only place gravity enters into this is just in this inequality. And actually, the main point of this talk will be trying to generalize this calculation to curved space, actually. And we'll see what happens to this bound as we do that. Okay, so this is a pretty interesting result. When I first learned about this, I found this quite interesting. And what it really says is that if you have a fixed volume of system, you're not allowed to really access all the states that quantum field theory would tell you typically that you could access, because most of those have so much energy that they would have caused the system already to collapse to a black hole. And as a result of that, the entropy is much smaller than the extensive result that you naively would have thought you would have gotten. Okay. So this seems to suggest that there's a gap between the entropy of ordinary matter and the entropy of black holes. So here I've plotted in the vertical axis entropy. The horizontal axis is area A of some configuration. And all the matter-like configurations which aren't black holes are bounded above by some curve which only grows like A to the 3/4, whereas black holes are on this line, which is a straight line in units of area. And if it's true that there's a gap here and there's nothing between these ordinary matter configurations and black holes, then it suggests something interesting, which is that if I want to know what is the most likely way or the most numerous, largest multiplicity of ways to, say, form this particular black hole, it's much more likely that this black hole came from just a slightly smaller black hole that I added some energy to, as opposed to the collapse of some ordinary matter. In other words, the subset of ways of making this black hole, which come from just collapsing ordinary matter, is totally dominated by just taking a slightly smaller black hole and just adding some energy. Okay, and so if this gap is for real, then it says that something interesting about the number of ways of forming black holes. Okay, so as I said, most of this talk is going to be about generalizing this 't Hooft calculation to curved space. And here, the sort of physical content of what I'm going to talk about is really just, could be summarized just in this slide. So imagine that I have n particles of mass m. So I have a bunch of protons, for example. In general relativity, because the force is attractive, there's a negative binding energy, which on this slide I'm going to call delta. The ADM mass of a bunch of protons is in general less than n times m. So if I have a bunch of protons and I pack them together in some way, some observer at infinity who does some experiment to determine the ADM mass of this blob here at the center will get a result which is smaller than nm, and it'll be smaller than nm by this binding energy. And what's interesting about general relativity is that nm minus delta can be made almost zero. There are ways of packing the protons so that the resulting ADM mass is much, much smaller than what you would call the, quote, proper mass, or just n times the individual masses of the protons. So you can get this number to be extremely small. And that's actually been known in general relativity for a long time. But this suggests that the entropy can be made extremely large compared to, so let's suppose I now take this set of protons and I allow it to collapse to a black hole. I get something whose area is of order m squared from the Schwarzschild formula. And what's interesting is that I can make the entropy, which grows like n, very large relative to this m squared. So by having something in which delta almost exactly cancels nm, I could have something which, when it collapses, becomes a very small black hole, yet it started out with a lot of entropy. If, for example, each of these protons had 2 spin states, the entropy of the system would grow very fast. It would grow like n. Okay, so that's actually the crux of of what I'm going to do. I'm going to construct configurations in which the gravitational binding energy almost collapses the so-called proper mass of the original system. And so even though the system doesn't take up, if it were to collapse to a black hole, it would be a very, very small black hole. It has a tremendous amount of entropy. Okay. So in order to do this analysis in curved space, we have to do it in a general relativistic framework. We're going to consider, for simplicity, spherically symmetric configurations and a metric which is of this form. So the only non-trivial elements of the metric are GTT and GRR. The main object that we're going to vary in this is the density profile of our system. So our system is just a spherical blob. It'll have some finite radius, capital R. So the stress energy momentum tensor will just be 0 for little r greater than big R. And we're free to arrange the shape of this profile for values of little r between 0 and capital R.
The stuff has some equation of state, and the equilibrium will be dictated by that.
In order to maximize, so this just determines things like the geometry of the space. But in order to maximize the entropy, what we'll do is we'll take the system at a microscopic level to be represented by some thermal system. And so that'll give us a relationship between the proper energy density and the proper entropy density. And then that'll let us compute the entropy of the object.
You'll be looking at the equilibrium configuration.
It's not.
The forces are balanced.
So no, actually, we don't. The object itself is not static. So we construct it, but when you let it evolve, it will do something strange like collapse to a black hole. But what we want to count is the number of initial conditions that are distinguishable that we can build. Okay? And that if each of those evolves forward in time, it should produce, at least if you were able to see the internal states of the black hole, a distinguishable black hole.
It sounds like you're starting with something you could characterize as being in local equilibrium, even if it's not global equilibrium.
Correct. In order to maximize the entropy, if you were to take any particular shell or a little box inside this region, that will be in equilibrium. So that will be characterized by a temperature. It should be clear on the subsequent slides. I haven't really gone far enough. Now, one of the useful object that will appear in all our formulas is roughly speaking, the mass within radius r. That's just given by this integral over rho. You'll notice something funny here. In this integral, the metric doesn't appear. It's just the integral of rho over r over what appears to be a kind of flat geometry. And it turns out that'll actually be the ADM mass of the object. The reason that this has this has quite a simple form, and the reason the form is so simple is actually because of the negative binding energy. The negative binding energy conspires such that the actual ADM mass is given by this integral and not the proper volume integral. And I'll say more about that in a minute. Okay. Another object that will appear in our analysis is defined here. Epsilon of r is just given by 1 minus 2m of r divided by r. When epsilon is close to 0, that means the object is close to being a black hole. Okay, and if epsilon is close to 1, then the space is pretty flat. Now, it turns out for our assumptions, if we also make the additional assumption that the matter is initially at rest, so I think in GR they often refer to that as a moment of time symmetry. So basically, the forward time evolution for that instant in time is the same as the backward time evolution of the system. If that's the case, then you can show that GRR is simply given by epsilon inverse. And you can also write an expression for GTT, which I won't exhibit because it's a little bit complicated. But GTT is also completely determined by this function epsilon. Okay? And the main point of this is, again, just to construct, by choices of rho of r, construct good initial configurations. We want to count distinct initial configurations and see how many such configurations we can have for some fixed value of mass m. Okay. So now we need a formula for the entropy. There are lots of ways of getting this formula. Here's one using Stokes' theorem. So what you can do is you can pretend that you have a conserved entropy current. It's not important to my calculation that really there's no dissipation and that entropy is absolutely conserved, but this just lets you construct the current. So you pretend first that you have a conserved entropy current. That might be the case if you have some dissipationless fluid, perfect fluid or something. Then you can write, by taking a space-like slice, you can write an integral over the entropy density. The result you get, this looks rather complicated, but the result is actually very simple. What it really amounts to is an integral of the proper entropy density. So that's the entropy density seen by a free-falling observer over the proper volume. And so once the metric GRR is determined, this is actually just the proper volume of the system. Okay. So there are two key formulas that we're going to use here. One is for the ADM mass. And that's an integral of this type. It's just given by the density function integral integrated over what looks like sort of a flat volume measure. And the entropy, which is given by the integral of the proper entropy density, but integrated over the proper volume. And the point of the calculation is that these two volumes can be different. The proper volume can be much larger than this sort of flat space measure if you adjust the system just right. Okay.
Rho r prime is T00 in a rest frame?
It's T00 for a free falling, for a stationary inertial observer, correct. And same thing with S. Okay. So now to maximize, yeah.
Let me clarify that. I mean, what do you mean by stationary inertial observer in this context where I have a dynamical system?
So so I've given you well, I haven't given you the formula for GTT and GRR, but GRR I've given you, and GTT one can solve for in terms of epsilon, and then therefore in terms of rho. So I have the full metric for the system. You can always go to, by equivalence, you can always go to some reference frame where G is canonical, 1 minus 1 minus 1 minus 1. That's an inertial frame. Rho and S are as observed by someone who's in that inertial frame.
I mean, are you assuming the metric solves Einstein's equations with T mu nu, depending on rho?
Say that again?
Are you assuming the metric solves the standard Einstein equations with some T mu nu, depending on rho?
Yes. I mean, it is true. So at the initial instant in time, the metric that we consider does actually solve the Einstein equations. We're not that interested in what happens. Well, we won't look in detail at what happens much later in time after our initial configuration is built. I'll characterize what happens, but we won't solve the equations forward.
You're saying a configuration solves the constraint equation?
It does. It solves the constraint equations.
So what you're calling inertial is an observer sitting at constant r in coordinates where constant r means a fixed surface area, a fixed area of all those points that are constant r?
I think that's right. I have to think a little bit.
So it's important that what's relevant here is that we can't have a system that's radiating in particular gravitational waves.
That's correct. That's correct. Yeah. Okay. So in order to relate rho and S, what we'll assume is that the system, at least at any local point, is characterized by a temperature. So in that case, rho scales like t to the fourth, the entropy density scales like t cubed, and really importantly, most importantly, what we want is a relationship between S and rho, and S scales like rho to the 3/4 power.
So you're assuming ultra-relativistic matter.
Yes, correct. So you could just say it's a ball of photons. It's a photon gas, and we've carefully arranged it in this way. And the goal is to maximize S while holding M fixed. And the question is, how big can you make S for fixed M? And you'll notice I don't say extremize S. So there's a difference between maximizing and extremizing in this case. It turns out that if you look at configurations, this is just some configuration space, and this is S. There are local extrema of the action, of the entropy, and these turn out to be static solutions. So these turn out to be things like solutions to the Oppenheimer-Volkov equation. So they're just static stars. But you can also find sort of pathological things in which the entropy just goes off to infinity, and those are the things that I'm going to talk about. Okay, so they're not actually extrema. They're never extrema because you can always perturb them in some way and increase the entropy more and more. These are stars. These are weird, monstrous things. Okay. Right. Now, the reason I can do this, of course, is that if I adjust my configuration in such a way that epsilon is very small, I can get a very large proper volume for the system, even though all the quantities like the temperatures and the energy densities and entropy densities are all finite and very smooth and well behaved. What I end up doing is I end up curving space in such a way that the interior of my object has a tremendously large volume, even though the entropy density and the energy density are all finite and well behaved. When I sum them all up, I can get a huge amount of entropy in here, but the binding energy keeps the ADM mass fixed. Okay, so So if you were to visualize it, this is not a space-time diagram. This is just a picture of the space on that particular time slice, and it has this huge proper volume, even though the surface area is fixed. Okay? So that's this trick. The trick is to try to come up with a configuration for which epsilon r is kept small for some very large subregion. Okay? And after we finished our paper, we realized that some similar things had been constructed in this earlier paper by Sorkin, Wald, and Zhang. So actually, a lot of the formalism, the stuff that I'd done in the previous slide, had actually already been done by these guys. Okay, so let me give you an example of a monster, and there are lots. It's very easy to construct examples. This is just one. We have a couple in our paper, and Sorkin et al. Also have a couple more in their paper. So this one I just call the blob, and we take the energy density to be some constant value, say rho 0, up until some core radius. All the large effects that I'm going to get are in the region between where this core ends and large, where r approaches capital R. And so I don't really care too much about this core radius once I set it up. It will not dominate the integral. And then I take rho to fall off like 1 over r squared outside the core. And if you go and calculate what epsilon is doing, so in this core region, the mass inside is just growing like rho naught r cubed. And what we do is we adjust it so that at r naught, m of r naught is close to, 2 times m of r naught is close to r naught. So that means epsilon is close to 0 at that point. So epsilon starts at 1 at the core. It sort of falls. There's some value, epsilon naught, that it achieves at r naught, which is already small. And then by choice of this rate of fall off, we get this rate of fall off for r greater than r naught. So this is now falling off like 1 over r, and then it stops at some point. And these objects are always finite, so everything just drops to 0 at the edge. So at little r equals big R, everything just goes to 0. Okay? So you could complain a little bit that I have some slight discontinuities here, but those things can be easily smoothed. There's nothing pathological about this arrangement of matter and energy. There's no place where there are rapid changes in the energy density or the temperature, et cetera, et cetera. So from that perspective, they don't seem particularly monstrous. Okay. So then we plug into our entropy equation. And so this is the sort of flat-looking part of the measure. This comes from epsilon to the minus a half, and the entropy density is just rho to the 3/4. If I count positive powers of r, I have r cubed from here and r to the 1/2, so I have 3.5 positive powers of r. If I have rho dropping off like 1 over r squared, then this drops off like 1 over r to the 3/2. And if you count it up, you get something that scales like capital R squared when you do the integral. And there's also a factor of 1 over square root of epsilon naught, which I can control just by choosing how close I want to make this relation to exact at the point r naught. Okay? So what's interesting is this is a matter configuration. It goes beyond what Tufte did because it's in curved space. It can have area scaling for its entropy. Furthermore, S can be made as large as you want because you can make epsilon not very small. If I take a slightly different scaling for the drop-off of rho naught towards 0, as I move away from this little core region, I can change the scaling of this. And so I can actually make this growth with capital R faster than r squared. I could get, for example, r cubed or r to the 2.5. And so I seem to be able to get something which has more entropy than the black hole that it will collapse to once I let it run forward. Okay? So there seem to be more matter configurations. If I count them all up, the number of them will be at least as large as e to the s. There appear to be more of those than there are supposed to be black hole microstates. Okay. So what happens to these monsters? You can ask a bunch of questions like, you might suspect that the thing, well, because epsilon never really hits 0 anywhere in this monster, you might say it's not a black hole, but it's very close to being a black hole. So you might ask some questions like, well, is there a trap surface here? In other words, if I have light emitted, null vectors, things traveling along null vectors emitted from the surface of this thing, are they focused together? Actually, when these things are initially formed, no, that's not the case. There's no trap surface. Eventually, there is a horizon. Eventually, these things will become black holes. And you can actually make a statement that if you look at the future, the sort of forward light cone of points that are inside the monster, for most of that region, the future of those regions does not include future null infinity. So it is something very funny. It's sort of a proto-black hole. It's something that's going to become a black hole, but depending on what your definition of a black hole is, it's not a black hole at the instant that it's made. One way you can analyze all this is by using something called the critical escape angle.
Did you say most of that region?
Yeah, there are points sort of near the surface of this thing, which if you look at the future of, say, this point might get to scribe plus. But if you pick a point in here, it's not going to get to scribe plus. Even though at the instant when this thing is originally built, there's no trap surface here. But when you run it forward a little bit, eventually you'll see that this thing is behind a horizon. And I'll give you a physical argument for why that's true. So there's something in general relativity called the critical escape angle, which is often used to describe things like neutron stars or objects which have pretty strong gravitational fields. And conveniently, this critical escape angle just up to some order 1 geometrical factor basically just scales like this same function epsilon that we defined. And the way it works is this. If you're on the surface of a neutron star and there's some value of epsilon at this point, if you emit a photon which is exactly directed radially outward, it can get to infinity. But if the angle that photon makes with the normal, with the radial vector, is larger than this critical angle, then it will enter an unstable orbit and it'll eventually spiral into the neutron star. So as you land on a neutron star, if you're looking toward the rest of the universe as you land, the part of the universe that you can see sort of narrows. And when the neutron star actually becomes a black hole, you can't really see anything as you hit the horizon. Okay? So this geometrical angle is useful for us because if you consider, remember the interior of this is supposed to be, in order to maximize the entropy, it's supposed to be at least at any local point a thermal system. So these velocities of the different particles are random. If you analyze what fraction of the particles, for example, in this little box here, could actually make it out to infinity, it's determined by epsilon. And when epsilon is small, virtually all of these guys are going to spiral inward. So you can make a kind of mean field argument that says that there has to be net inward energy flow in this object. And since it's fine-tuned, the object is fine-tuned so that for everywhere outside the core, epsilon is already close to 0. If the energy flows inward, then epsilon will eventually be driven to 0 and negative. So essentially, it's pretty clear that most of this object is going to become a black hole. Now, another interesting thing you learn from this kind of analysis is that this object has to also evolve into a black hole if time reversed. So imagine I do a time reversal. I run this object backwards in time, so I reverse all these arrows. Well, since it's a thermal system, reversing the arrows doesn't change the overall behavior very much. And so this is something that becomes a black hole if you evolve it forward in time, but also becomes a black hole if you evolve it backward in time. And so that's very weird. That means that if I were to try to create this object out of some previous initial data, so I go to some time before the time slice that I used in the initial analysis, somewhere if I go far enough back, there has to be an initial singularity. And in fact, there has to be a white hole. There has to be something that just spits out particles with sort of infinite velocity. So future evolution of this monster is a black hole. time-reversed evolution is also a black hole, so that means that somewhere back here there's actually a white hole, if I were to view it, the whole thing moving forward. Okay, so that's why we call them monsters, because they're very strange objects. Okay, so now you can ask the following question. You can say, well, are these monsters buildable? So in other words, suppose you had arbitrarily advanced technology, but you had constraints coming from fundamental physics. To what extent could you really build one of these monsters? And one interesting buildability condition that you might impose is you might say, well, as I'm setting up my desired density function, remember I get this huge entropy because I'm able to fine-tune this epsilon to be close to 0 and keep it there for a long period of time. You could ask a question like, well, if I'm trying to build this, construct it using machines, perhaps I shouldn't be able to adjust where the particles are to a distance much better than the thermal wavelength. Okay? And so if I ask, well, would a small fluctuation in your position by a thermal wavelength, suppose that were enough to drive epsilon negative at a particular point, and I might say, well, that means it's not buildable. That means that the contractor who's building it somewhere along the way will actually accidentally perturb it, unavoidably perturb it, or it will fluctuate, and it'll become a black hole before it's done. Okay, so that's one condition you might guess is part of a buildability condition. Certainly not all the conditions you can impose. If you impose that condition, interestingly, you get the bound s less than a. So if you plug this condition into the integrals that I had on the previous slides, you find that the entropy can't exceed a. So it seems that one can't build monsters with entropy greater than a. Now this is a, again, back in Planck units. So up to an overall factor, this is a reassuring inequality because it says that you probably can't violate the black hole entropy bounds by building one of these things.
So isn't it fair to say this is far more than a buildability constraint? This is a limit about where your description of the physics completely breaks down because of quantum fluctuations.
Well, so I would say this is a little bit more of a buildability condition because this sort of characterizes the inevitable fluctuations in epsilon that come from the fact that you want it to be a high entropy state that is thermal. We tried more fundamental things. Like we said, suppose there's a fundamental Planck length. And suppose that we impose that r epsilon of r has to always be greater than that Planck length. Then you get that's a more, I would say, more fundamental limit on this object. Because at that point, you're really asking questions about quantum gravity. There you actually don't get such a strong limit. You get s less than something like a to the 2.5 or something. So it doesn't quite get you to this point, but that is an even more fundamental limit, I think, than this one. Okay. So I do think, so let me say it another way because it's relevant to what I'm going to say on the next slide. This is a buildability condition. I can't imagine a civilization being able to regularly build objects that violate this bound without having them first become black holes as they're in the process of building them. But there's another question which I'm going to address on the next slide, which is even though you couldn't really build one of these things, is it a legitimate state in the Hilbert space for gravity plus photons? And for that, then you should be able to apply these things like, well, you can't resolve distances less than a Planck length, and so maybe that's a more fundamental constraint on what's even in the Hilbert space. Okay, so but even the buildable ones close this entropy gap. So the ones that look to be buildable actually close this gap between this Tooft curve of a to the 3/4 and where the black holes actually sit. So that if these things are legitimate objects and can be exist in some sense in the theory, then it is no longer true that the most entropic way to get to this point is to just slide along this curve. In fact, one could have a monster built and then the monster collapses to the black hole. Like
Do you have anything to say about the coefficient of area in what you just showed us?
that. This one? You mean in this bound or?
Yeah.
In this bound, I think it comes out to be, so as I said, in the same Planckian units that we usually express s equals a to the a over 4, this coefficient is of order 1.
Okay, but so it could well be above the black
Right.
hole.
It's a little, for this kind of very rough analysis, it's very hard to be confident in what that numerical coefficient is. Okay. Right. So I sort of argued that it's hard for me to imagine that civilization could construct as initial data a monster that has entropy greater than A. However, that doesn't completely get us out of the problem. So imagine that you start with some collapsing spherical shell of energy. It has ADM mass m, and suppose the other quantum numbers q and j for the whole configuration are 0. So you arrange this collapsing shell of energy so that it has the same quantum numbers as one of the monster configurations that I built. In fact, it could be the same quantum numbers as a monster configuration that has S much greater than A. Okay? So naively, you would think there's some non-zero probability for the initial state to evolve or tunnel into this monster state. Even if I couldn't directly construct it to begin with, there should be some non-zero overlap or some non-zero amplitude for this evolution. If that's not the case, then you have some kind of selection rule here, which is a new kind of selection rule, in which you're forbidding certain transitions between states in the Hilbert space, but which have exactly the same quantum numbers. Usually in quantum mechanics, when we say there's an exact restriction preventing state A from evolving to state B, it's because A and B have some different values of quantum numbers, and those quantum numbers commute with the Hamiltonian. So usually we have a very good reason for that kind of selection rule, and in this case, it's a little hard to understand what that reason would be. Okay? And as I mentioned, this brings up the question of how big is the Hilbert space for gravity. So imagine, and of course it's semi-classical gravity because I'm not really doing quantum gravity here. So if I have semi-classical gravity, you might imagine that if I take a nice space-like slice and I consider the set of possible matter fields and I consider the set of possible geometries, that should give you some sense of what the Hilbert space is. And the existence of these monsters suggests that the dimensionality of this Hilbert space could be much larger than e to the a. Okay, or at least you have to think about whether that's the case. And of course, this is sort of bad for holography and all kinds of other things. Okay, it's bad, for example, for the ability to identify the microstates of the black hole because we believe that the number of microstates is of order e to the a over 4, but if the Hilbert space describing things that might evolve into black holes is much larger than that, then you have a little problem of interpreting what these calculations mean. Okay. It's also kind of problematic for ADS-CFT duality because, for example, let's suppose I'm in anti-de Sitter space, but on some small scale I construct a monster. So it's just, you can imagine that what the monster does is just determined by local dynamics and doesn't really matter whether at long distances I'm in anti-de Sitter space or just flat Minkowski space. So I could imagine constructing the monster and the calculations would look more or less just like the ones I've shown you. And the question is, the point is, if there are these monsters which have entropy much larger than A, how could they possibly be described in the boundary conformal field theory, which the dimensionality of that space is, or the number of degrees of freedom of that space is just scaling like A. Okay, so it seems like there just aren't enough degrees of freedom in the boundary theory to describe these monsters. Now, this is actually related to something that was considered by these guys, Steve Schenker and some other guys back in 2006. What they considered is the following. They considered a thought experiment in which you have some metastable vacuum which is pretty close to a true vacuum, and you live here, and you try to excite a bubble of this phase inside this phase. That problem was studied a long time ago by Alan Guth and also by Andre Linde, and the thing that happens is if the bubble gets big enough, you get an inflating geometry which is attached to a flat geometry. And from the outside observer's perspective, this looks like a vacuum bubble that's collapsing, false vacuum bubble that's collapsing. From the interior observer's perspective, it looks like an inflating de Sitter space. Okay? And these guys considered whether in string theory one could have in the landscape some two vacua close to each other that look like this, and some humans that evolved here are trying to create a bubble configuration here. And one thing I should say is that in the original studies by Guth, it was shown that this thing also has to have a past singularity. So in other words, in order to create this, if it were just to evolve forward from some initial data, that initial data would also have to be singular. What they resorted to in their case also was to say that the way to create this would be to create some initial data that looked like a big false vacuum bubble, and maybe it would tunnel through to this configuration. And there were even some calculations by Polchinski in which he calculated the tunneling rate for what if you did have a initial big enough initial false vacuum bubble, what the rate would be for it to tunnel through and create this inflating universe. So that was pretty well studied actually some time ago. These guys noticed the same problem. They said, well, if this type of thing is possible in this string theory universe, then there's a problem with ADS-CFT because it would be very difficult to describe all the degrees of freedom that are potentially, you know, in some sense, infinite number of degrees of freedom that are inside this inflationary bubble in terms of some boundary conformal field theory. And they came to a pretty radical conclusion. There's a whole bunch of steps in their analysis which I won't go into, but they conclude that the interior of this thing is described by one boundary. They draw a Penrose diagram which actually has two boundaries. It's like I think the same Penrose diagram for a big short-shell black hole in ADS. And what they conclude is that the boundary theory describing, the boundary description of this is a mixed state, which involves correlations between states which are inside and states which are outside. And they claim that since their logic is the following, since the initial state which evolves to this can be constructed as a pure state in ADS, and yet this final state is a mixed state, and pure states cannot evolve into mixed states, they conclude that this is just strictly forbidden. So they claim in ADS space, even if the local string vacuole looks like this, one could never produce such an inflating pocket universe, is what some people call it. Okay? So that's a pretty strong conclusion. I don't know if it's right or wrong, but it's also advocating for a new kind of selection rule in quantum gravity, one in which the fact that quantum amplitudes are zero is not driven strictly by conserved charges, but for some dynamical reason you get a zero. Okay. So I really don't know whether I don't know really whether that's true that there are such selection rules or that this kind of thing is a problem for ADS-CFT. It could be, in my mind, it seems plausible that maybe ADS-CFT doesn't tell you very much about what's back here, and maybe ADS-CFT just gives you information about what's in the ADS space up to this horizon, but perhaps not behind it. So maybe that's another interpretation of all of this. Here's a very heuristic argument for how you might get a selection rule which is sort of purely dynamical in nature. So it's not based on symmetries or conservation laws. So imagine that you have, let M be a state in your Hilbert space which represents a monster with very large entropy, S greater than A. Let psi be some smooth initial data, like a collapsing shell, which would evolve into a black hole, and that black hole will have the same quantum numbers as the black hole that the monster state would evolve into. And this hypothesis that there's a selection rule is basically that psi, the forward time evolution of psi, always has to have exactly zero overlap with M. So for all values of t, this overlap has to be zero. Okay, and that's a conjecture. That's what Schenker and these guys are saying in their paper. Maybe one way to justify this is you could consider evolving both M and psi backwards in time. So choose some value of the time parameter capital T, evolve M backwards in time, evolve psi backwards in time, and you find something interesting. If you evolve psi backwards in time, remember psi was just some collapsing spherical shell or dust ball. If you evolve that backwards in time, no matter how far back in time you go, you just get something smooth. You just get a bigger and bigger and less dense shell. However, these monstrous configurations, or equivalently these pocket universe type configurations, if you evolve them backwards in time, for some choice of capital T, you eventually hit some singularity. You hit this white hole. And you actually can't, in some sense, you can't evolve the thing further back than that because you hit that singularity. So perhaps it's the case we could just slip in calculating this overlap, which we would like to be zero for all little t. Perhaps we just slip in. Let's assume that these three operators commute. Okay, we slip this in, and we can rewrite it in terms of a question whether this very smooth initial time configuration, which represents the early time dust ball, can evolve into this highly singular. If we choose t just so, can evolve into this highly singular thing. And so maybe this is a kind of dynamical selection rule that just says that very smooth things can't evolve into highly singular things, and doesn't rely on symmetry. It relies on dynamics. as I said, this is very heuristic. I'm not claiming this is correct, but it's one way of thinking about this. One problem with this is this sort of many worlds thing, which is that when you have some initial data, some state in your system, which you say looks like a monster or looks like a dust ball, when you really evolve it using the full quantum mechanical Hamiltonian for the system, you sort of get all the possible many worlds branches in there, in that wave function. And some of them, you could imagine, don't actually have the singularity. So you could imagine that if you chose the branches of this many world wave function where, for example, all of the particles which are in this dust ball are sort of as far away from each other as possible, then maybe there's some branch of the wave function where you don't even have a black hole. So you have a collapsing dust ball, which semi-classically makes a black hole, but in the quantum wave function, you have some branches where there's no black hole. Or similarly, when you evolve this thing back, you maybe have some branches that don't have that initial singularity. Because everything I did so far was pretty semi-classical. And so there's sort of a, right away, there's sort of a many worlds problem with understanding what's happening here. But I always have that problem when I think about gravity or cosmology. Okay. So, wow, I got through that pretty quickly. Just to summarize, one can at least mathematically construct objects which have a lot more entropy than a black hole of equal mass. That has, depending on how you interpret that, that has a lot of implications for topics like this. Whether one can, in principle, actually physically construct such objects is unclear, and it's also unclear whether they're really sort of legitimate objects in the Hilbert space for gravity. But I think the answers to those questions are quite interesting. So, thanks.
So you are starting with a formulation that says it's appropriate to describe your matter as some sort of relativistic fluid in local equilibrium.
Yep.
That description automatically comes with limits on its domain of validity.
Correct.
And I would certainly argue that the first and foremost such constraint is that the scale of variation of a macroscopic quantity like the energy or the entropy density must be much, much larger than the de Broglie wavelengths of the excitations that are actually carrying this energy density. And in an ultra-relativistic fluid, that amounts to the same thing as your buildability condition. That the scale of variation has to be large compared to 1 over the 4th root of the energy density. So it seems to me that there's a very appealing but more conservative interpretation of what you've told us, which is the configurations which satisfy what you're calling a buildability constraint, but I'm sort of seeing as basically the domain where it makes sense to believe anything in this analysis. Gives you configurations with entropy less than the area, less than order 1 constant times the area. That's a very nice conclusion. And that if you violate that constraint, why should I believe it?
I think
so basically, my question is, why shouldn't I just be happy with this more conservative interpretation?
Well, that may be the case. The extent to which these things are weird, if I try to push S greater than A, is that I require that this epsilon get very, very close to 0. So close that if I were to shift, so r times epsilon of r is really just the proper length. So because r is just a coordinate. So this is really a proper length. And what it says is that if I were to be uncertain as to the my position inside the distribution by 1 thermal wavelength, it might drive epsilon to be negative.
Right.
Right.
And isn't that exactly the same thing as violating the condition I tried to sketch that says your basic description of your matter makes sense?
Well, I guess I would disagree with that, because I could certainly, if I wanted to construct so here I'm coarse graining everything because I want to characterize it by some temperature or something, right? But suppose I said I really want to describe I have some huge number n of photons in here, and I want to describe the individual. Let me forget about the polarizations, but I want to describe the. Actually, momenta is not good because I want localized things, but I want to describe the little phase space, little wave packet descriptions for each of those photons.
Yep.
Then I certainly can build lots of configurations which violate this inequality, okay? And there doesn't seem to be any fundamental thing wrong with that particular configuration, as far as I can tell. I'm not pushing things where I try to specify the location of a photon to within a Planck length. That's a different thing. That I would regard as a really sort of fundamental restriction. But when I look at the sort of Fock space or sort of wave packet basis representation for states which violate this inequality and give S greater than A, I can't find anything about that particular configuration which I say, well, this is obviously unphysical. It is true that a typical fluctuation of that thing could drive, in a particular place, or in a particular shell, could drive epsilon negative. But I don't see why the particular snapshot, that particular element of the Hilbert space that I'm describing is itself unphysical.
If you look at a configuration that has S parametrically larger than A, are you not violating the condition that the radial derivative of the energy density divided by the energy density, that's 1 over the scale of variation, aren't you violating the condition that that be much, much smaller than the thermal wavelength?
I'd have to check, but I think the answer is no. So I think I can build these things with very, very slow variation of t with respect to r, and I don't get crazy unphysical things like that. This condition is very different from conditions on the rate at which t varies with r. This is a condition on how close to the Schwarzschild radius the thing really is. And other restrictions like, oh, I just don't want big derivatives or things like this in these curves, those don't give me anything, actually.
Maybe so. Okay.
Yeah.
So suppose I was to consider one of the static balls, the one that you drew as a top.
Right, like a star.
Right. And one that was at the edge of the gene's instability bound.
Yeah.
So that if you made it a little more massive, it would collapse.
Yeah.
Okay. If you compare the entropy of that object with the entropy of the black hole that
Tiny.
would collapse to,
Tiny.
that's 8 to the
Tiny. All of these extremal guys are on a curve which is a to the 3/4 you can prove. And so those are ones which give this gap between this gap. Yeah.
One more question, please. If you did the same analysis for the same question but with dust, do you know what the answer is? With zero pressure? Would it parametrically change?
You mean our whole analysis, or specifically this one?
The top, yes. That
Dust and cold dust.
Yes, zero pressure.
Zero pressure, I think probably you're very far from optimality in A. So I think you get something much smaller than a to the 3/4. So.
You know, in the ADS CFT correspondence, if you just try to put stuff in ADS, after a certain energy density, it's dominated by Hagedorn matter.
Okay, right.
Not gravitons.
Okay.
Okay. So you start heating the stuff up. First it's gravitons, then becomes Hagedorn matter, whose thermodynamics is that of dust.
Okay.
And so if you start approaching black holes in that way from ADS CFT, the appropriate analysis would actually use the equation of state of dust.
Interesting. Okay. But that suggests there would be well, I don't know, maybe there's something special about ADS that I don't quite understand, but that would suggest there's a big gap in between those configurations and the, yeah. Any other questions? Well, I actually had an hour and a half. I guess I